So most of the statements that we're interested in proving in an analysis course are of the form P implies Q. Prove that if P, then Q. And there are three main strategies, three avenues through which we can do that. We call them a direct proof, and then two forms of indirect proof, the contrapositive proof and the contradiction proof. These two sort of masquerade as one another a lot, very commonly. So I want to try to draw the distinction between how those two forms actually look different. So the direct proof is probably the one that people feel the most comfortable with in practice. In order to show that P implies Q is true, P implies Q is true whenever the premise is true, we're guaranteed that the conclusion is also true. And so a direct proof goes straight ahead and says, let's assume that the premise is true. So as soon as I assume that the premise is true, we've ruled out all the vacuously true cases for P implies Q, and now we only have to prove that if we assume P is true, then Q must necessarily also be true. And so direct proof has the form, we're going to assume that P is true, and then demonstrate to you why Q must then also be true. So the truth of Q is deduced, it's pulled out of the proof of P. Right? So as an example, suppose that I have this statement, let n be a natural number. If the third power of n is odd, then n itself must have been odd. So that's an if-then statement, right? We can see it right here. So P, the statement P here is n cubed is odd. The statement Q is n is odd. And so the first thing I would do if I'm trying to discover a direct proof for this is I would write down the assumption that P is true. So assume n cubed is odd. And then I would write down the last line of my proof. Therefore, thus, Q is true, n is odd. And so whatever else goes into my proof, if I'm writing a direct proof, I know that it's going to begin with this assumption, assume n cubed is odd, and it's going to conclude with this deduction, this conclusion, thus n must be odd. And of course, all of the interesting stuff happens in between, right? But at least the main structure of the proof will look like that. And structuring your proof carefully is at least half of the battle in writing a successful proof in any course, in an analysis course in particular. So a direct proof is going to have that shape to it. Meanwhile, a proof by contradiction goes the other way around, and it seeks to prove an equivalent implication to P implies Q. So an equivalent implication to P implies Q is the contrapositive implication, not Q implies not P. So that's what, when I say the word contrapositive, that's what I mean. The contrapositive of P implies Q is not Q implies not P. So it's not possible for my conclusion to be true unless my premise, it's not possible for my conclusion to be false unless my premise was also false, right? That is an equivalent statement to P implies Q. And so a contrapositive proof is a direct proof of that equivalent implication to P implies Q. You reverse the order and you reverse the truth values of the premise and the conclusion. So in the contrapositive, we first assume that the conclusion is false. So for this statement here, if n cubed is odd, then n is odd. If I assume the conclusion is false, I'll say something like assume n is not odd. Which, of course, since, if we remember the definition of odd and even, we'll write assume n is even, right? So we assume that the conclusion fails. And then we endeavor to show why the premise must therefore have failed. Because the only way that P implies Q is not a true statement is if somehow the premise is allowed to be true and the conclusion false. So if the conclusion is ever false, we need to know that the original must have been false as well. And so a contrapositive proof, we would have to deduce the fact that n cubed is not odd. Thus, n cubed is even. Right? And there's details in the middle that we would need to fill in. But again, I recommend anytime you're trying to write a proof to get this sort of basic scaffold of the proof out of the way so that you know what it is that you can take for granted, the stuff highlighted in purple. We're just going to be able to assume that those things are true, apply definitions of even and odd, for example, and then try to work our way towards drawing the conclusion that's written in green down here at the bottom. And finally, the famous proof by contradiction. So to write a proof by contradiction, we end up starting with an even stronger assumption than we had when we were talking about the direct proof or the contrapositive proof. We assume the exact opposite of the thing that we're trying to prove. We're trying to prove that P implies Q is a true implication. So in a contradiction proof, we start by assuming that in fact it is not. Sometimes, just to underscore the silliness of what we're doing, instead of using the word assume here, often we'll use the word suppose. It kind of tells the reader to, let's suspend disbelief for just a minute. Let's entertain the possibility that this thing that I'm claiming is true actually was not true. So we suppose P implies Q is false. Now remember, for an implication to be false, as we were saying just a minute ago, an implication is false when its premise is true, but its conclusion is not. So P and not Q. So that's how most proofs by contradiction begin, is they begin by this supposition. Suppose that the premise is true and also that the conclusion is false. One of the nice things about that is it gives you more material to work with as the proof author. So you'll say something like here, suppose that my premise is a true statement. So suppose n cubed is odd. But then I also get to suppose a second thing. I get to suppose that my conclusion was false. So n is even. So I get sort of two things that I get to assume are true when I begin a proof by contradiction. The degree of difficulty, though, is what is it that you're supposed to then do in a contradiction proof? You're supposed to arrive at a statement which is logically consistent with our assumptions, but which we know for sure is absurd, right? Nonsense. And the form of an absurd statement in classical logic is R and not R. We have to show that there exists a third logical proposition, which is in fact not a logical proposition at all, because it's both true and false, right? And that's the one thing that doesn't happen in classical law of excluded middle logic. So we often don't know what this R is when we begin writing a proof by contradiction, but we hit on an absurdity. Find something which we know is not true, and yet we have deduced it to be true somehow in the process of writing this proof. And so then we say something like, this is absurd, so P implies Q, or something at the end, right? Proof by contradiction is a very popular proof strategy because it can be very exploratory, right? You give yourself two things to work with, two assumptions of truth, and then you just sort of play around with them and smush them together and see if in the process of deducing other true statements for them that you end up with a statement that you've deduced logically from that material, but which you know for sure is not true. This is the classic example, is the proof of the irrationality of the square root of 2, which is one of your workbook exercises in this section. You begin by making the contradictory assumption that, well, suppose the square root of 2 is actually a rational number. Then you do a bunch of work and show that then this implies that, the definition of rational number is violated in some way, right? So these are the three main proof scaffolds, and filling in the details I'm not as interested in today, but I do want to give you the last 5 minutes of our time together to work on in groups, see if you can figure out how to apply the definitions to fill in the gaps between premise and conclusion here. But as I say, often more than half of the battle of getting a solid proof written down on the page is just to start by writing sort of what I've written here, right? Write out what is the assumption that you're trying to make at the beginning, that you get to make. The things written in purple here are things that we get to assume if we're going to write a proof that takes these forms, right? And then write the conclusion you're trying to reach down at the end, which you don't get to assume is true, but which you have to show why it connects, why it follows logically from what we did assume in the beginning. And if you get that written down, you're often a lot of the way towards having a good proof. Usually the gap in between is just taking a definition, like the definition of what it means for a number to be odd, and then looking that up. So as an example, just to wrap up, switch over to my browser here real quick. If I'm trying to write a proof that is predicated on a definition of even, well, I would pull up, what does it mean for something to be even? Well, the definition of even is actually an existentially quantified statement. There exists an integer k such that n is equal to 2k. Right? That's what it means for n to be even. And so once you have the basic scaffold of your proof, you then apply the definitions that you're using, many of which have these existential and universal quantifiers in them. And then hopefully they show you can apply them to both ends if you want to, and see how they kind of meet in the middle. It's a very common way to discover a proof of some of these elementary number theory and analysis statements.